The geometry of shadows. How a wiggle doesn't change the result. This study explores a fascinating geometric shortcut. The idea that the swirling movement around a closed loop is exactly twice the area it captures. By bridging abstract vector theory with interactive simulations, it reveals that even when a path wiggles or twists into complex three-dimensional shapes, the final physical result often depends only on the flat shadow it casts on the floor. The journey from theory to verification. The power of twice the area. The sheet begins with a simple but profound observation. For certain types of movement, you don't need to do complex calculations along a path. Instead, you can simply look at the surface area inside that path. In a perfectly flat world, like a circle on a sheet of paper, the circulation or total swirl around the edge is consistently and predictably twice the area of the disk itself. This establishes a mathematical shortcut that turns a long journey around a perimeter into a simple measurement of the interior. The mystery of the wiggling path. To test the limits of this rule, the study moves into the third dimension using a saddle loop, a shape that looks like a Pringles chip or a mountain pass. One might expect that because the path moves up and down as it goes around, the result would change. However, the analysis proves a beautiful symmetry. As the path climbs up, it eventually has to come back down in a way that perfectly cancels out the vertical influence. This means the final value is determined entirely by the flat projection, the shadow, of the loop. Whether the surface is a flat disk or a rippling bowl, if they share the same shadow, they share the same circulation result. When the force varies, the sheet then shifts from pure geometry to more complex environments where the wind or force field isn't uniform. In these scenarios, the swirl is no longer a constant multiplier. By using color-mapped visualizations, the study shows how local interactions between the force's strength and the surface's tilt create a unique scalar result. This transition moves the learner from basic geometric rules to the sophisticated tools used in fluid dynamics and electromagnetism, bridging the gap with computation. Finally, the sheet concludes with numerical verification. Since perfect circles and smooth surfaces are often mathematical ideals, the study uses discrete polygons, essentially approximations made of many small, straight segments. The convergence. As more points are added and the segments get smaller, the rough approximation begins to smooth out. The proof. The simulation demonstrates that the ratio between the path's movement and the captured area steadily approaches that ideal value of 2, proving that the abstract theory holds up in the messy, practical world of computational physics.